Howdy, howdy, howdy. We're talking equivalent fractions yet again. And this time we're actually going to find ways to create our own equivalent fractions without having to draw a whole bunch of darn shapes, because that just takes a lot of time. Now, that being said, though, shapes are nice. They're our friend because they give us a visual representation of what is happening. And as we've said many times, we are visual creatures. We learn by seeing things. So with that being said, let's do some visual stuff first. So you're going to see a lot of questions that ask this. Hey, what fraction does this represent? Now, the easiest way of doing this is, well, one, make your fraction line, easy peasy. The easiest way of doing it is counting every single shape. So how many shapes do we actually have here? Well, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12 total. Remember, the total amount of something, that is always going to be your denominator, the number that goes on the bottom. So I've got 12 total, boom, on the bottom. Now, let's say the question was asking, hey, what's the fraction of purple? Okay, well, let's count how many purple there are. 1, 2, 3, 4, 5, 6, 7, 8. So this diagram shows 8/12ths, right? I wouldn't say 8/12ths, 12ths, right? We really want to have that th sound at the end, 8/12ths, okay? Awesome. So this diagram absolutely shows 8/12ths because there's 12 total and 8 of them are actually purple. Now, is that the only fraction that this diagram represents? Well, actually, no. What we can do is we can actually group these. I noticed that this whole column right here, yeah, these are all kind of that gold yellow color. So if I just circle it, I'll circle that for now. Let's see what else happens if I circle this column. All right, and I'll circle this column. So rather than looking at each and every single one of these octagons, now I can think of this just in terms of columns. Well, how many columns do I have total? I've got 1, 2, 3 columns total. So 3. Okay. Out of those columns, how many columns have purple stuff in them? 1, 2. 2/3. So not only does this group of shapes show us 8/12ths, at the same time, it's showing us 2/3. Kind of neato, right? And we would say that since we didn't change how many octagons there were or anything, we would say that 8/12ths is equivalent to 2/3. They're showing the same exact value, and yet they're two separate fractions. And that's why we call them equivalent. They're the same. So equivalent, equal, boom. Now, you might be thinking, well, I don't like drawing shapes every single time, and I don't blame you. Neither do I. So what's a symbolic way, a way to use numbers to make this a quicker process? Well, let's have a look at our numerators here. 8 and 2, what's the relationship there? How would I go from 8 to 2? You might be thinking, well, that's easy. I'd go 8 subtract 6. But whenever we're working with equivalent fractions, we don't want to use addition. We don't want to use subtraction. And I'll explain that in a later lesson. But for now, no, we're not using addition or subtraction. So that leaves us with multiplication and division. So how do I go from 8 to 2? Well, if I divide 8 by 4, that would give me 2. Okay, well, what about on the bottom? How do I go from 12 to 3? Yep, you betcha. I divide by 4. And this makes sense visually with our diagram here, because notice how many shapes are in each of our columns. We've got 1, 2, 3, 4 in each of the columns. So essentially what we've done is we've just divided this whole thing by 4. And that gives us our equivalent fraction. Okay, if I worked backwards, 2/3, how do I go from 2/3 to 8/12ths? Well, hey, backwards, I love that word. Inverse is another way to think of it. What's the inverse here? Well, to go from 2 to 8, I would have to go times by 4. And 3 times 4 also would give me 12. Okay. Now, there's another way I can even think of this. What if I wanted to find another equivalent fraction, but this time I want to make it bigger? Well, what if I cut all of these octagons in half? Okay, I'm just finishing up cutting all these. I didn't want to waste your time. So boom, I'll cut these guys. Cool. So now instead of thinking of these as full-on octagons, I'm going to think of them as half octagons. Well, how many half octagons do I actually have? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 22, 24. I've got a total of 24 half octagons. And how many of them are purple? 2, 4, 6, 8, 10, 12, 14, 16. So I would say I've got 16/24. Okay, 16 out of 24 or 16/24. And check it out. Look how this works. How would I go from 16 to 8? Well, I'd divide it by 2. How would I go from 24 to 12? Same thing. Divide by 2. Cool. And this works. This makes sense because I'm splitting each octagon in half, right? I'm essentially doubling the amount of octagons, or rather doubling the amount of items in this diagram that I'm counting. Now, one routine we definitely have to lock in. Notice whenever we're going from one fraction, making it into an equivalent one, whether we're multiplying or dividing, the numerator and the denominator are being divided or multiplied by the exact same number. Okay. If I went 8/12 and I times the top by 10 and I don't do anything with the bottom, that's going to give me 80/12. And that's a completely different value. These are not equivalent to each other because now I've got a bigger numerator than my denominator. And as we saw in the very first one, my numerator was smaller than the bottom one. So these would not be equivalent. We have to make sure whatever you multiply it by or whatever you divide it by, it has to be the same on both the numerator and the denominator. 80/120ths, yeah, you betcha. That's equivalent to 8/12. So long story short, I'm going to wrap this up for you nice and easy. Whenever you're making equivalent fractions, it's actually a pretty easy job. Because if they give you 1/2 and they're like, hey, make an equivalent fraction, you can multiply the numerator and denominator by literally any number you want, just as long as you're doing it with both the numerator and denominator. So for instance, let's go, 500. Why not? That's a fun number. And again, we're multiplying the numerator and the denominator by the same thing. 1 times 500 is 500. And 2 times 500 is, 1,000. So 1/2 is equivalent to 500 thousandths. Kind of cool. And if you really wanted to see that visually, it would look something like this. Okay, so I've got 2 squares. Okay, one of them is blue, the other one is orange. Okay, so 1 out of 2 is blue. There we go, there it is right there. And if I'm timesing these both by 500, it's as if I cut it into 500 pieces. So obviously that's going to be really hard to do, and that's why I'm not going to do it. But that's what it would look like. I would be cutting this into 500 tiny little chunks, okay? And still the ratio, after I've cut both of these squares by 500 times, it would still be 500 over 1,000 total little chunks, okay? So easier way to make equivalent fractions, you just multiply or divide both numerator and denominator by the same number, and presto, you have yourself a new equivalent fraction. All right, I hope that was helpful. Have fun.